And you got into derivatives a little bit, I think, if I remember correctly. And so we're going to start off with limits. Everything we do in calculus is in some form or another really based off what is a limit and what do we do with it and what does it all mean. And so let's talk about the notation for a limit. Is it okay if I dim the lights just a tad?
Yeah.
Feels like, yeah, let's go with maybe, sorry, pardon the, how about that? Is that okay? Okay. I don't like feeling like it's like a surgery room or something, with the bright lights on everything. Okay, so the notation for a limit is this, of course. LIM, and then the little X with an arrow, and then maybe some number, like a 2, and then there's always something, bless you, there's always something we're finding the limit of. So it could be some function like f of x or g of x or whatever. So how do you read this? Limit as x approaches 2 of f of x, or limit of f of x as x approaches 2. It's the same thing, just like a slightly different order. So we want to be able to read this correctly and sound like we understand what we're talking about. I'm not going to grade you on that, of course, but you want to be able to communicate what you're trying to say. So the next question down there at the bottom is a really fundamental question. We'll take a few minutes to talk about this, because I feel like students that come from pre-calc are decent at finding limits, like they can do some of the mechanics of it, but when I ask that question, they're kind of like, I'm not as sure about that, right? What is a limit? What is a limit? So what kind of the most common wrong conception here is that a limit, so take a look at that limit I wrote up there, limit as x approaches 2 of f of x. A lot of people would say, oh, well, that limit right there, if I were to evaluate that, it's just f of 2. Right? Let's just plug the 2 in for x and we'll call it good. And that is definitely not correct. Definitely not correct. Let me define this with words, and then I've got a really silly, illustration for you that hopefully will stick. So what is a limit? A limit is the pattern of behavior. Pattern of behavior of the y values as x gets close or closer and closer to a specified value. You'd say it kind of the other way. You could say as x gets closer and closer to some specified value, we're looking for the pattern of behavior of the y values. So in certain instances, just plugging in the 2 is going to work. Those are special cases. Like if you remember from the video last night, and by the way, there's no quiz today. Don't take that as any kind of a pattern that there will never be videos. There could be one at any time. We're just not going to do one today. So if you remember from the video, there are well-behaved functions, right? They're continuous functions, and so in those situations, just plugging in whatever that specified x value is, that's going to work. But most functions are not like that. At least most of the ones we'll look at are not like that. And so just plugging in a 2 is not always going to work. So let me give you an illustration of what a limit is, and I'm going to use my iPad as kind of a sacrificial lamb potentially here. And so I'm just going to set it right here on the floor. It's probably pretty tough. I'm sure if I jumped on it once, maybe it'd survive, but if I jumped on it a bunch of times, maybe it would have a problem. But there's my iPad right there. I'm standing over here, and so you're going to be paying attention to the pattern of behavior of my movement, okay? So I start walking towards the iPad. Think about me like dropping breadcrumbs as I walk. It would form a little graph of the way I'm moving. So maybe some breadcrumbs would come over here, and then, I'm getting a little adventurous. So I'll come over here. I'm dropping breadcrumbs the whole time. Can you picture my graph? So I'm dropping all these breadcrumbs, and I'm cozying up to the iPad and getting closer and closer and closer and closer and closer. I'm getting right here, and right here I jump over it, right? Because I don't want to step on it. And then I keep dropping breadcrumbs, and I walk over here, and I walk over here, and da-da-da-da-da. And you can see that if you only paid attention to my pattern movement, you'd see that over there I was headed for the iPad. I jumped over it, so I never actually stood on the iPad. And then as I walked away, I kept on dropping breadcrumbs. So you see the pattern of movement away from the iPad. Similar, right? So whether I'm approaching from that way or this way, both directions, my pattern of movement was towards the iPad. So you could say, if I stop dropping breadcrumbs, you could say that the limit as, I approached a certain time, say it took me 10 seconds to get there, of my movement. So the limit Actually, let's go with a t right there. So the limit is my time approach 10 of my moving around would equal the iPad, right? Because my pattern of behavior was towards the iPad from this side, and then from this side was also towards the iPad. But did I ever actually stand on the iPad? I did not. So if we said this, my movement or position at t equals 10, what would the answer to that be? Error or DNE, undefined, because I never actually was there, right? So we would say that, you know what, he never actually stood right there, but his pattern of movement from both sides was towards the iPad. So when we think about my pattern of movement, that's a limit. That's the concept of a limit. This is the old concept from back in like Algebra 1 and Algebra 2, like if you plug something in, what do you get out? So if you plugged a 10 in, you get nothing out because I was never there. But if you look at the limit, you can see, okay, he was headed towards the iPad, headed towards the iPad, so the limit of his position was the iPad. That makes sense? So I'm definitely going to put a lot of effort into helping you understand what a limit is and what a limit is not. And at this point, stupid examples, silly examples are probably best, right? They'll stick in your mind. If you can just remember the iPad, that I didn't actually step on it, yet my limit was the iPad, that's a good distinction between what is the value of a function versus what is a limit. Okay? Okay, so we're going to use a couple techniques here to evaluate limits. Numerical, using a table, this is a pretty useful thing. It's kind of nice because if you've got a table made for you, then it doesn't take a whole lot of calculating. You're just looking for that pattern, right? The pattern of whatever the function's doing. There's graphical. Again, graphs are super duper nice because all you got to do is look at the graph and look at the pattern of motion, like me dropping the breadcrumbs. And then there's analytical. We might have to do a little bit of algebra to be good at that. That make sense? Okay, cool. So we're going to look at these right here. Let's take a look at numerical. And I want you guys to grab your calculators, and we're going to make a table here to help us understand this one. Situation. We see this first example here. Example A, limit as x approaches 0 of that. Well, you know, we talked in the video a little bit about those well-behaved functions. This is not a well-behaved function, is it? Because if you did try to just plug the 0 into that function, what would happen? Yeah, you'd get something over 0, and that's an issue. You'd get an error, and we'll see that come into play here. So we're going to use a table to help us with this. And so I'm going to show you, just to remind you in case maybe you've forgotten a little bit about how to do this. You know what, this is left over from yesterday. So I'll start over and just show you how to do this in case maybe you've forgotten. The first thing we're going to do is we're going to enter that function. Let me move this over just a little bit. We're going to enter that function right there into our y equals menu. I'll show you hopefully a couple of useful tricks here throughout the year with calculators. So we're just going to go x over, and you've got to put parentheses in there, square root of x plus 1 minus 1. And there's the function I'm supposed to be evaluating. And so I'm going to look at a table. And so one of the ways we can do this is we're going to go second table set right there. And what might be a wise number to start our table at? Like I would say, in my opinion, I think we should probably start the table at the target number for our limit, which in this case is 0. So I'm going to start the table at 0. And then, are you guys all familiar with what delta table means? Right, it's like how you want the table to progress, like how big the jumps are. I've got it set at 0.01 right now. I think that's pretty reasonable. Although if you wanted to do 0.001, I think that works too. And so at this point, I'm going to go to my table, and I'm going to scroll back a little bit, something like that. And this is a good example of me and the iPad, because you can see that when x equals 0, as you all predicted, the function doesn't exist. There's the error, the calculator error, because you're dividing by 0 at 0. But when you look at the pattern of behavior to the left and the right of 0, you can see that the y values, 1.97, 1.98, 1.9899, 1.99, error, and then beyond that, 2 point something, right? And so intuitively, what would you say? What would you estimate the limit to be? 2. Now you can't say that definitively, right? Because what if somebody came to you and said, you know what, I think the limit is 2.000000001. Could you really defend that it's 2 instead of that? And if you maybe tightened up the table a lot, maybe you could count that answer out. But we typically operate in this world where the problem has been designed to work nicely for you. So 2 would be a very reasonable answer, and that actually is the answer. We could prove that analytically if we wanted to. So do you see how the pattern of behavior is headed towards 2 from both directions? So we would say 2. I'm not going to fill out the table here on the on the screen. If you want to do that, you're welcome to do that, but I think the calculator suffices there for you. So just a little note there, again, just to kind of reinforce this again, whether the function exists or not at 0 doesn't really matter in regard to the limit. It's all about the pattern of behavior to the left and the right. Okay, so let's take a look at B. Let's see if you guys, maybe based on what you've done in the past, can answer these. We've got the limit as x approaches 1 of g of x, and the limit as x approaches negative 3 of g of x. Take a minute, look at those, write down what you think the answer is, and we'll see what you got here in just a second. This is all based on a graph. This is like me and the breadcrumbs, right? We're just looking at all these little breadcrumbs that were dropped and where are they headed and what do the limits look like. One little note about graphs like this, please assume integer values. Please don't look at a graph like this and be like, well, it looks like the limit's going to be -1, but it's just like a tiny bit over -1. So I'm going to go with negative 0.99998. Just go with -1. Assume an integer value, and that'll be happy. A lot of the graphs I'll create in like Desmos or something, and those are about as perfect as they can be. Every now and then there's like slight little variations, and so it's like, well, just go with the integer value. Don't make it more complicated than it needs to be. Okay, so let's see here. Alexandra, did you think about that first one, limit as x approaches 1? Would it be 1? Okay, let's write that down really quick. All right, well, at least. Limit as x approaches 1 of g of x. Alexandra is saying 1. How do you guys feel about that? Do you agree with her? Is there any disagreement? What about this? Do you see how somebody might put this? Maybe put DNE. Why would somebody put DNE there? Because there's a hole, right? So something is DNE at 1, and what is DNE? The function itself, right? Yeah, so the function doesn't exist at 1, right? And so that for sure is true, but the limit itself is 1, because remember, the limit is not concerned about is it there, it's simply concerned about what was the pattern of behavior around that little x value, and it definitely is 1. Okay, cool. And then limit as x approaches -3. Cody, what do you think about that one?
I got 2.
I'll just put this up here, equals 2. And yeah, if you look at the graph there, this is probably the case where somebody could argue, hey, I think it's 2.1, but it's closest to 2, right? So I think 2 certainly makes a lot of sense. All right, so I'm hoping that was good for you. Do you have any questions? We all happy with that? Okay. Good deal. Let's move on. C. There's a little graph, and if you were paying attention to the summer assignment, you saw a graph kind of like this on the summer assignment. So this says limit as x approaches 3, and then it defines f of x to be a piecewise function. I want to be really good at these piecewise functions. Can anybody describe, just in general, what this piecewise function is going to look like?
It would look like x minus 2 is a little dot at x equals 2.
And x minus 2 is?
X minus 2 is it's like y equals x. Should be down to it.
It's a line, yeah, exactly. Yeah, so it's just a line with a little bit of a hiccup in the middle of it, right? Yeah, you got it exactly right, Matt. Okay, so x minus 2, the y-intercept is -2, the slope is 1. So I will do my best to draw this in. So let's see here, x minus 2. I'm going to start off right there, and then we're going to progress like this. So then, of course, right there you can see I left a little break in the graph, right? So right when x is 3, we're actually going to have an open circle because that line only applies for all numbers other than 3. And then when x is 3, y is 5. And Matt kind of got at this a little bit. What's the other piece going to actually look like? That's the main piece, right? The other piece will just be what? A dot, a point, right? So when x is 3, y is 5. So 1, 2, 3, 4, 5 is right there. And there's your graph. And so from that graph then we should be able to analyze this limit pretty quickly. So as we get closer and closer to 3 from the left and the right, what is the pattern of behavior of the y values? Feel free to shout it out if you think you know it. approaching 1. So if you think about, if we were just kind of walking along this line from this direction, aren't we getting closer and closer to a y value of 1? And then if we do the same thing over here, we're getting closer and closer to a y value of 1. And so the limit would equal 1. So I'll just say limit as x goes to 3 of f of x is equal to 1. Well, let me play devil's advocate a little bit here. What if there was a second question in this group? And what if the answer to the second question was 5? What would the second question have been? Not f of x, f of 3. F of x at 3, right? Yeah, so if I told you the answer was 5, the question probably would have been f of 3. F of 3 equals 5. So this is a case where you can see that the pattern of behavior was different from the actual limit itself. And we'll talk pretty soon about how that is an indicator that the function is not continuous when the pattern of behavior does not equal the value of the function. And you can see from the graph it's not continuous, right? See the little hole and the point up there. So we'll get onto that stuff later. But at this point, I'll keep asking you this. I hope that you'll get comfortable asking questions. It's an important thing that you be able to voice concerns or just confusion or anything like that. So you all look pretty confident, though. That's a good thing. Okay, awesome. Moving on. So it is possible for limits to not exist, and there are 3 different reasons that could happen. The first one you probably heard of quite a bit last year, different behavior from the left and the right, this thing. Right? So that's a possibility. Unbounded behavior, and then the last one, not something we'll make a real big deal about, but oscillating behavior is another possibility as well. So let's take a look at D, and we're going to be using a graph. And so if we're going to be using a graph, it might be useful to graph this. Believe it or not, this exact graph, this absolute value of x over x, showed up on the AP test last year. Just sort of, unexpected. I mean, you never know exactly what to expect, but it showed up. And so hopefully if it shows up again, you'll remember this. But absolute value of x over x, you can plot some points. Does anybody know what this looks like? I think there was some element of this on the summer assignment. Isn't it like one step? Yeah. Like this kind of? And so if you do plot some points, you should be able to come up with this. But we'll do it fairly quick here. Here is your y-axis and your x-axis. And if we were to graph this in a lovely orange color, it would look something like this. You'd have a y value of 1 with an open circle, and then you'd have a y value of -1, another open circle, looking something like that. And I'm going to label my graph with a 1 and a -1, and there you go. It's basically you're dividing some number either by itself or by its opposite the whole time, so the outputs are all going to be plus or minus 1. So when you look at this limit, this is one of those limits that fails to exist. And so if you were to write an answer to this, you would say DNE, but I would want you to be able to answer, at least at this point in kind of a general way, what would be the reasoning for DNE on this one? The different behavior thing, right? You've got two different values as you approach from the right or the left. And so it's a DNE for that reason. I do want to say that if you were, for right now this is fine. But there's a better way to do this. So if you just say, there's different behavior from right or left, that's a good description, but we're going to talk about a better way to do that. So please don't use that necessarily as like a justification on, say, a quiz or a test. We'll kind of build this out a little bit further as this chapter goes on. So don't hold on too tightly to that. We'll kind of let that one go and use some better notation to make that case later on. Okay, so E. Limit is x goes to 0 of 1 over x squared. Maybe use your calculator here, generate the graph. I mean, if you already know what the graph looks like, that's great. But if you don't, use your calculator to generate the graph. And we'll talk about that particular limit as well. So when you graph this, like, what do you see? What does the shape of the graph remind you of? Any takers? You got it on your calculator. What does it remind you of? silence. That's not what I came up with. Oh, what do you think?
Like a tree that you can't see the top of. So it's too tall.
Oh, it just goes way up into the sky. Yeah, okay, I like it. It's like a perspective drawing. That's cool. I see the Atari symbol. Do you see that? Those of you that are like, know about Atari from back in the day? Yeah? I also see a volcano. Do you see that too? Kind of a volcano looking thing. So I'm hoping that your graph looks like this, where we've got something like that and something like that. See the volcano now? There's even a little hole for the lava to come out. Yeah, okay. It's okay to be silly. I'll be silly all the time. Whatever. You can be all stoic and serious if you want. It's just calculus. So what do you think? This limit, as we approach 0, let's think about what that volcano actually means, right? Like, what is the left side doing? It's going up and up and up, right? Like we're heading towards like infinity, right? So you got a vertical asymptote right there at 0, and so the closer you get, the steeper the graph gets, right? It's just going to go up, up, up forever. We're talking about infinity. Same thing on the right, right? And so infinity, contrary to popular belief, is not really a number. It's a concept, right? It's a concept of numbers going up and up and up and up without bound. And so we have an unbounded limit. And so it would be very easy and reasonable, I think, to write this. The limit doesn't exist. The reasoning being we have unbounded behavior. I do want to let you know that in the very near future, by the end of this chapter, instead of calling that unbounded behavior, we'll call like a graph like this, we would say that the limit is actually infinity. So I'm going to say dne or infinity. The reason being that when you put dne, that's kind of a general way of putting it. We get that it's going up and up and up forever, but infinity is actually a little better description because isn't the behavior kind of the same from the left and the right? From the left, we're going up without bound. From the right, we're going up without bound. And so I think infinity describes it a little bit better than dne. But, you know, like in a free response situation, if you put dne, I definitely would give you credit because you're right. Because infinity is not really a number, it's a concept. Okay, we good with that? All right, last one is the crazy oscillation graph. So take a minute, use your graphing calculator, graph sine of 1 over x. Maybe you did this last year. This is in most calculus and pre-calculus textbooks. Take a minute and graph it. We'll talk briefly about what it means. This is not something we're going to spend a lot of time with or dedicate much quiz or test space to. Something like that. And then the classic trick, once you get this graphed, yours looks sort of like mine, or mine looks sort of like yours. Yours is better because it's on a graphing calculator. But the trick here, of course, is that if you start zooming in, usually when you zoom in, don't things get simpler? You can like see, okay, we're down to just like this one nice little line, blah, blah, blah. But on this one, when you start zooming in, doesn't it get worse? Try it. Zoom in on the origin if you haven't already done so, or maybe you have done that in the past. You start zooming in on the origin, instead of fewer lines, you get more lines. And you keep zooming in over and over and over again, and the lines just get more and more steep and more of them. And pretty soon it starts looking like a barcode, on something you'd buy at the store. And it is kind of confusing, but I want to explain why this is. What is the range for sine? Like, what are the y values? What does it go between on the y values?
1, -1.
Between 1 and -1. Okay. So we know that this is going to oscillate between a high of 1 and a low of -1. But then that 1 over x is kind of interesting because we're doing this limit as x goes to 0. Let's think about what 1 over x does. Let's make a little table here. We'll come back to this throughout the year, but this is a good time to start talking about this. If I make a little table with my x values and 1 over x, let's think about what 1 over x does as x goes to 0. So I'm going to start us off really easy. We're going to make a table. So if x is 1, what is 1 over x? 1, okay. So I'm making x approach 0. So maybe another logical thing to use, I'm going from 1, I'm heading towards 0. So I'm going to go with 1/10. Do you see how I'm heading towards 0 on the x values? From 1 to 1/10. So if x is 1/10, what is 1 over x? What is it? It's 10, right? It's just the reciprocal. So, okay, so as we started to edge towards 0, the y value went up to 10. Well, I'm going to get closer to 0. How about 1/100th? Wouldn't it be 100 for the 1 over x? Just the reciprocal every time. Well, let's fast forward a little bit. How about 1 over 100,000? I'm getting a lot closer to 0 now. What's the output? 100,000. Okay, so the closer I get to 0, what pattern are you seeing with the outputs? They're getting huge, and eventually you think about it, like, what if we did 1 over a billion or 1 over a trillion? Well, now it would be a billion, a trillion, and we start adding, how about a 1 with a trillion zeros after it? Right? Wouldn't it just be the reciprocal of it? So we're getting huge without bound. We're talking about infinity, aren't we? Okay, so as 1 over x gets closer and closer to infinity, what is sine doing? Well, sine starts getting confused, because remember, it's going to oscillate between 1 and -1. 1, -1, 1, -1, 1, -1. So as that output gets huger and huger, then it starts vertically jumping almost between 1 and -1. So remember, a limit has to have the same behavior from the right and the left. And so is it 1, is it -1, or is it 1 or -1? Which one is it? Which one is it? We can't decide, so the answer is D and E. Make sense? It's a hard one to really just like say, oh yeah, I've got it all, right? Infinity, not the easiest thing to just grab a hold of, but that's the pattern that's going on. Okay. Oops. Come on. So you see, this is where the video started. I really sincerely do hope that you watched it, and I also sincerely hope that when you watched it, you're like, oh yeah, did this in pre-calc, not that bad. Not all the videos are going to be like that. The vast majority of the videos are going to be like, gosh, never saw that before, glad I watched it. Okay, this one, you probably did a lot of this in pre-calc, that's fine. Okay, so you go through these nice, well-behaved functions. They're so sweet, look at them. That one right there, do you see the unit circle stuff? You need to be darn good at the unit circle. You do. If you hear unit circle and you think, gosh, I've never known how to do that, and I won't know how to do that, you will have serious problems. You just need to know how to do it. If you want help with it, happy to help you with it. A little check for understanding there, a couple more unit circle-ish type activities. And now we get to the not so well-behaved functions, right? The ones that are going to create a little bit of an issue for you, but these are always the interesting ones. And so we're going to spend a little bit of time with these. We'll spend maybe 5 to 10 minutes with these, and we'll finish with a little different activity and we'll be done. I will suggest, though, anytime you see a limit, I do think that it's good to just try to plug in. If you can just plug in and directly substitute, I think that's a great thing. Most of the time that's not going to be the case. Algebra is going to be a common technique. And then there's a different technique that you have not seen before that we'll learn a little bit later on this year. Okay, so let's take a look at the first one. Some examples here. Limit as x goes to -1 of x squared minus 1 over x plus 1. If you did directly substitute, if you said, you know what, I think this is well behaved, and you plug in the -1, what are you going to get? Undefined, right? You get divided by 0. And so then you got to turn to, maybe some of your algebra skills or maybe a newer skill that we'll learn later and ask yourself, what can I do to deal with this? And isn't the issue the x plus 1 in the denominator? Like if we could figure out a way to make that go away, then this would probably go all right. We'd be able to figure it out. And so what can I do to the top that might help towards that goal? Factor. Can anybody tell me the name of the type of factoring that the top is? Difference of squares. Great memories. Okay, so we would say limit as x goes to -1, and that factors as x plus 1 times x minus 1 all over x plus 1. And then, of course, the x plus 1's cancel. And we've just basically dealt with the part that was giving us the issue. And so maybe now we can try this direct substitution. So when we do that, what do we end up with? -2. So our limit here, the pattern of behavior is -2. Now, you got to understand, it's true that f of -1, like if that function was called f, if we said f of -1, that would be d and e, yet the limit is -2. Let's talk about why that is really quick. When you canceled out the x plus 1's, you were just left with this right here. What kind of a graph is x minus 1? This is a regular old line, right? Just like we looked at earlier. So if I were to graph this, here's what it would look like. I would have x minus 1. So here is -1, slope of, let's try that again, slope of 1. But then we're going to have a little bit of an issue at one part of the graph, right? Do you know where that issue is going to happen? -1. We canceled out x plus 1, right? And so when we get over here to -1, see right about there, we're actually going to have a hole in the graph. Anytime you cancel out a factor, it actually creates a hole in whatever graph remains. Okay? So we can see that what happens here is that f of negative 1 doesn't exist, because we can't pretend that that x plus 1 was never there, because it was there. But the pattern of behavior is still going to be based on that x minus 1 graph. From the left and the right, we're approaching negative 2. Let's see here. Do I want to talk about anything else there? I feel like I do, but I'm forgetting what I was going to talk about. Do you guys have any questions about that? You guys did do stuff like that last year? Maybe? Yeah? Okay, good deal. All right, so let's do this. I remember. This is actually really important. Did you guys notice this? You probably did. Did you notice that when I... Hang on just a second. Let me highlight something. So that when I don't know what the deal is. I'll just do this. When I did my second step, did you notice how this remained? I did some factoring, right? I factored the top, and that was useful, and I canceled some stuff out. But did you notice how the limit did not disappear? You guys understand this, I think, that in math, when you've got some symbol or some notation, when it's there, it's probably telling you to do something. There's some meaning attached to it, right? So whenever that symbol, whatever it is, that has meaning attached to it, whenever it disappears, isn't that a way of telling me that you did the thing that the symbol was indicating? Right? And so we want to be really careful about this. I notice students a lot they'll get excited because they're like, hey, I know what to do. I'm going to factor this thing. And they factor it and they do all this canceling. And in all that excitement, they forget to write that. So when you forget to write that, what are you communicating to me? I did it. I've evaluated the limit. And then, so that's, pretend the thing in the purple circle is not there. All of a sudden we just get this negative 2. And I'm just like, I know where it came from. But from a communication standpoint, I'm like, where did you get that? Where did that happen? If you leave the limit there, you're telling me, hey, you know what? I did a little factoring. I did some work on the inside there, but I haven't done the limit yet. And so then when I get to here, I'm like, oh, I know where they got the negative 2. They actually did the limit, because then the limit's gone, right? You've actually done what it told you to do. So from a communication standpoint, don't be lazy. Just write LIM with an X and a little arrow, and that's telling me that I still have yet to do this, and now I just did it, now I'm done. So please do that. This is the type of situation that's frustrating if this were a quiz question, and it looked just like this. I just erased that, right? We all know the answer is negative 2, don't we? You would most definitely not get full credit for this, right? Because it's a miscommunication. You're telling me, hey, I did the limit, but then I kind of didn't, and this negative 2 just shows up out of nowhere. I mean, where is x minus 1 really equal to negative 2? It's not. It simply is not, unless you did a limit. Does the communication thing make sense? Okay, so please do that. All right, so I think you can handle this, probably no problem at all. Will you guys try numbers 2, 3, and 4? 2, 3, and 4. So do those on your own, and we'll close up shop at that point. So done, we can kind of check these answers here as we go. I want to give you, hopefully, a good strategic thought here on number 2. Number 2 is, of this little set here, is probably the most challenging factoring because the a value is not 1. You can see that if you try direct substitution, you get the division by 0. So there's obviously an issue. But I want to just give you a thought here. So we have limit as x approaches negative 1. And we can see that the issue, the part that's causing the problem, is the x plus 1, right? So here's my thought. You might look at the top and you might think, man, I don't know, factoring was never my strongest thing. But if this is going to work, doesn't one of the factors in the top have to be x plus 1? So I'm just going to go ahead and put that there, not knowing if this is correct or not. I guess I do know, but originally I might not have a clue. Like, is this actually going to work or not? I don't know. And then I'll just make the other one, I'll just build the other one to be what it would have to be, right? So the first term is 2x squared, so why not just make this 2x? And the last term is negative 3, so this would have to be minus 3. You do a quick mental check and be like, all right, 2x squared, that works. Then you got 2x minus 3x. Hey, that works. So it worked out the way that I was hoping, right? You could just do, instead of like approaching the top as if you don't know what it should be, put what you think it might be and check to see if that actually does work. Just a thought. You don't have to do it that way. This does cancel with this. We end up with negative 5. Is that happy for everybody? Any questions? Okay. Number 3, similar issue with factoring. This time the factoring is in the denominator. What kind of factoring is it? How would you describe the factoring down there? Take out the x, undistribute the x, factor out the x, whatever. Those are all good descriptions. Again, notice I'm trying to model good behavior here for you. I got my limit as x approaches 0. In the top I've got 3x. Down here I've got x, parentheses, x plus 2 as I complete the factoring step. And you can see that the x in the top and the x in the denominator cancel out. That was the part that was creating the issue. Now when you plug in, you try your direct substitution. Did we all get that? 3/2 is good? Okay, awesome. And then finally, number 4, a couple of factorings here. Because if you try direct substitution, we have that same division by 0 problem. All right, so Austin, how did the top factor?
X minus 1, x minus 4.
I agree with you there. Okay. And then Matt Harrison, how about the denominator? How did that factor for you?
I didn't finish that one.
Okay, sorry. Preston, did you get that one?
X minus 4, x plus 2.
X minus 4, x plus 2. I think I agree with you as well. Notice that the x minus 4s then cancel out. We apply that limit as x goes to 4. We get 3/6, which would get full credit. Reducing fractions is not mandatory. Or, of course, 1/2. All right, I'm seeing pretty relaxed faces. That's good, right? Any questions? Okay, very good. All right, so I am done with that for the moment. Will you grab those 3x5 cards that I just handed out to you? Got a couple of quick questions for you. Kind of a